Hello all and welcome. My name is Joshua Bright. This class is Survey of Physics, and this presentation is called Carbon Nanotubes, or CNT for short. So the CNT pioneer is this man on the right. They were discovered in 1991 by this guy Sumio Iijima while he was a senior research fellow at NEC's Central Research Laboratories. He explains that it was a seemingly accidental discovery because he was researching fullerenes, which are a spherical carbon molecule, much like CNT, but just spherical. So not exactly accidental, just wasn't looking for it. But he was studying something that's a similar substance. But he said, while researchers in different countries were focused on the anode side of carbon electrodes for the mass production of fullerenes, he noticed a new material with a long, thin appearance when observing the cathode side. Now, the CNT basics, much like carbon fiber, because they are very similar substances, it has a very narrow diameter, but much more narrow than carbon fiber by a lot. It ranges from 0.8 to 150 nanometers, which you need a microscope to see. They have superior electrical and thermal conductivity. They surpass the thermal conductivity of diamonds even, due to their tensile strength being several times that of steel, but having a specific weight, that of 1/10 of steel. That makes it about 100 times stronger than steel weight for weight. And they have superior chemical stability. They do not react with acids and alkalis, which make them superior to most metals in regard to corrosion. And they're strong at extreme temperatures. They maintain their strength up to 1200 degrees Celsius. As a material still usable at high temperatures, its properties are difficult to match. Now, moving on to CNT synthesis. It's synthesized by using a dual pulse laser arc discharge device, kind of like this diagram over here. It's a very simplified diagram, though, for people like me. And they use graphite rods with a 50-50 catalyst mixture of nickel and cobalt at 1200 degrees Celsius in flowing argon, and then they dual pulse the laser. And after that, they heat treat the substance in a vacuum at 1000 degrees Celsius to eradicate carbon-60 and other fullerenes and kind of purify the whole thing. And then they repeat this process several more times, and usually it produces a yield of a greater than 70% purity. So that's one thing that they're trying to improve upon is the purity level at after this process. They could do better than 70%, they think. Now, what about CNT applications? So there's a lot of potential applications for biomedicine in CNT, such as drug delivery. CNTs are considered to be a resourceful alternative for transporting therapeutic molecules to the body. CNTs as a drug delivery vehicle have the ability to target specific tissue, allowing for overall dosages and side effects to be reduced. They can also be used in gene delivery, similar to the drug delivery method. By introducing nucleic acids to CNTs, there is potential to treat various diseases. CNT-guided nucleic acids can repair, replace, regulate, add, or delete genetic targets with a particular disease. And also, they have some potential uses in hypothermia therapy. Hypothermia therapy is essentially rising the temperature of cancer cells or tumor cells in order to kill them, because we've found that cancer and tumor cells are very sensitive to changes in heat, especially high temperatures. And CNTs have the ability to limit the heating to specific tumor cells, which protects other healthy cells. And they also have a potential use in cell separation and manipulation. CNTs are a potential candidate for use in detecting and separating circulating tumor cells, CTCs for short. They have a particular advantage of being guided and controlled by out-of-body magnets, which is pretty cool when you think about it. You can control their movements with magnets outside the body, which I would assume would take a lot of practice. And finally, something a little bit more fun, NASA's use of CNTs. So you've probably heard of Vanta Black. Well, NASA has used CNTs to create a black coating that can absorb 99% of visible light, probably a little bit more than 99%, but I don't think as much as Vanta Black. But they use the same process as Vanta Black. So the Vanta in Vanta Black stands for vertically aligned nanotubular array, which is the same method that NASA used. So it's the same type of substance, but I believe Vanta Black absorbs more light. And then there's also another substance that was created by a group at MIT that is currently holding the record or whatever for the blackest material. But the other cool thing about it, other than the 99% of visible light, is that it also absorbs 98% of infrared and far infrared light, which increases its possible absorption range by 50%, which is pretty crazy when you think about it. And the reason for this and the most promising use of this substance is to coat the inside of telescopes so that viewing far-off celestial bodies, such as orbiting planets, will be much easier. And that's pretty cool if you think about a lot of astronomers' missions and ideas of getting humans to colonize other planets that would help in identifying some other planets out there. And that's the end of it. A lot of the biomedical uses, here's my sources, a lot of the biomedical uses are theoretical. They haven't been extensively practiced or experimented with, but just based off of our knowledge of the material, they believe that these things could be possible. And thank you for listening.